In this video for our NMR lecture, we're going to be looking at complex splitting. So complex splitting occurs because sometimes coupling is more complex than our n+1 rule that we've looked at before. This occurs when the proton is coupled to two or more non-equivalent protons. And it tends to occur around alkene hydrogens, small cyclic hydrogens, and stereocenters, so stereogenic hydrogens. We can really think of complex splitting as using the n+1 rule in succession. And so an example of complex splitting is shown here, where we have two peaks that are split again into two smaller peaks. You can see this looks very different than the typical quartet we would expect if we saw four peaks in the NMR. If you remember, your quartet should look more like this. So now let's look at how this complex splitting arises within the molecule. So if we look at an example of methyl acrylate. Methyl acrylate has an ester and an alkene. The alkene has three protons on it: HA, B, and C. These three protons are all different from each other, so they show their own signal in the NMR spectra, as we see here. We can also see that they don't follow the typical n+1 rule with their splitting. Instead, they follow the complex splitting rules and complex splitting patterns. And so you can see, looking at HA, B, and C in the zoomed in versions, they all look slightly different from each other. And if you remember talking about the coupling constants, we can utilize the coupling constants to determine which of these peaks correspond to which hydrogens in the NMR spectra. And so to understand this complex splitting pattern and the successive n+1 rule, it's very useful to draw splitting trees. So with our splitting tree, we start with a single hydrogen, and if it has no neighbors, we know it shows us as a singlet. If that hydrogen is then coupled to one hydrogen, that singlet would split into two and make a doublet. So this is kind of our tree branching out. Instead of just the single one up here, we can think of it as the trunk. It now has two branches on it. So if that hydrogen now sees two hydrogens that are different from each other, it's going to split into that doublet like it did for the original hydrogen A. And then it's going to take that doublet, and each one of these peaks gets treated like its own splitting pattern. So I'll take the first peak, and it gets split into a doublet, since there's one HB. And then the second peak, that gets split into a doublet as well, since it's one HB. So this is when our hydrogen kind of sees HA, and this split down here is when our hydrogen sees HB. And then, so let's say we have another hydrogen that it sees. It can couple to multiple hydrogens this way. So our hydrogen will see HA, HB, and now HC. So we've already seen what happens when it sees HA, it makes a doublet. When it sees HB, it takes that doublet and splits it into two doublets, which is how we get our double doublets. When it sees HC, it again is going to treat each one of these lines separate from each other. So it'll take that, our first peak, split into a doublet, take our second peak, split that into another doublet, take our third peak, split that into a doublet, and take our fourth peak and split that into the fourth and final doublet. So this happens when our hydrogen sees HC. We end up with a double-double doublet. So that means when we look at an NMR spectra and we look at what the peaks would look like for this. We know if it's not coupling, we get a singlet. If it couples, we get the doublet. If we get another coupling, we get the double doublet. So that's 4 peaks that are all about the same height. And we designate that DD for double doublet. If we get something like our third one here, the third use of the N+1 rule, we get a double double doublet. So we get 4 peaks and another round of 4 peaks. So we have 8 peaks total for the double double doublet. And now keep in mind with our splitting, it doesn't have to just turn into doublets. If HC here, if there were 2 HCs, then it would split into a triplet at the end. So you can end up with various combinations, and splitting patterns like this do get very complicated very quickly. But just remember, when you're looking at an alkene and you're looking at that double bond, use the N+1 rule in succession. So do N+1 rule with 1 hydrogen, then go to the next one, N+1 rule again, then go to the next one if there's a next one, N+1 rule. And the easiest approach to the complex splitting is to break it apart and just use the N+1 rule over and over. Don't try to do it all at once. Do it in steps like this. It makes it a lot easier. And so let's look at an example of a real NMR with the N+1 rule. With our methyl acrylate, if we examine HC, HC has HB next to it, and then we can see 1, 2, 3 bonds away is HA. So that means HC in our NMR spectra sees HA and HB. So when we look at the actual peak, we can see we start with our singlet. That gets split into 2 when HC sees HA. And then that doublet gets split into 2. And that occurs when HC sees HB. Now it's typical convention to start with the ones that have the largest coupling constant and work your way towards the ones with the smaller coupling constant. Doing it that way, it's easier to draw your splitting trees. But so you can see in our real life NMR, we have 1, 2, 3, 4 peaks. And the distance between these 2 peaks and these 2 peaks, that is that 1.5 hertz. And then the distance between our second peak and our fourth peak, that's our 17.4 hertz. And looking at our coupling constants here, the 1.5 tells me most likely it's a geminal coupling. Because remember, geminal hydrogens typically are between 1 to 3-ish. And then looking at that 17.4, that tells me it has to be a trans coupling. Because remember, trans couplings are typically between 11 to 18 hertz. So since I know what the coupling constants are, I can tell that this is a trans hydrogen. And so it's really with these double bonds that the complex splitting and the coupling constant helps you figure out the cis-trans configuration. So looking back at our full spectra for methyl acrylate, we can see we've interpreted the HC NMR peak. HB looks really similar. HB will see HC and it'll also see HA. So it has a geminal coupling constant and a cis coupling constant. Remember, cis tend to be smaller than trans, and we can see that in the distance of the peaks here is less than the distance of the peaks for HC. And then looking at both their geminal peaks, the geminal peaks look like they're about the same size. And then finally, looking at HA, we can see HA is cis to HB and trans to HC. So it's going to have a cis coupling constant and a trans coupling constant. So we can see that in our peaks here. The cis coupling constant is the smaller one on the inside there. And you can see that's about the same distance as we see in HB. And then the trans coupling constant is on the bottom here. And that distance is about the same as we see for HC. So you can see the coupling constants match each other. So we can say HA couples with HC, HA also couples with HB. And so it's looking at the close zoomed in pictures like this that we're able to determine our cis-trans configuration. And so now you guys should be able to use the n+1 rule in succession to explain and predict complex splitting. And remember, complex splitting typically occurs around double bonds. It also can occur around stereocenters. But for our class, double bonds are the most common time we see the complex splitting occur.